Hi friends, welcome to our YouTube channel Bright Education Center. We are going to discuss the chapter Electromagnetic Induction for grade 12th physics syllabus. On competitive examination analysis we are going to do it. So the major concepts and the equations of the chapters are like this way. In this one, what is magnetic flux? We'll discuss the first. And what do you mean by electromagnetic induction? Some lower classes you might heard about this one, like whenever there is a change in magnetic field lines around a material, a conducting material, there will be an inducing of current in the conductor. That means a current is produced in a conductor whenever there is a change in magnetic field around it. This process is called electromagnetic induction. This is only the basic concept of production of electricity by using a generator. So what is this flux and what is electromagnetic induction? How it can be induced the EMF? That's the major concepts of this chapter. First, what is magnetic flux? Magnetic flux is the magnetic field lines passing perpendicular to a surface per area. Phi is equal to B dot A. B is the magnetic field intensity, A is the area vector. And this A and B has an angle theta between them, then we can write phi is equal to BA cos theta, where theta is the angle between area vector and magnetic field. You should remember it, area vector has a direction always perpendicular to the plane of the surface. Area vector will be, so BA cos theta. By using that concept, we can find the flux phi. Now, whenever there is a change in flux with respect to time, Michael Faraday says that there will be an inducing of EMF. Faraday's law states that induced EMF E is equal to negative d phi by dt. This negative stands for the direction of the EMF. Induced EMF will be always in the opposite direction of the changing flux. That is given by Lenz's rule. So phi E is equal to minus d phi by dt. D phi by dt, it can be change in flux by time taken also. We can do one question regarding this way. A question is like this. The magnetic flux of 3 into 10 raised to minus 4 Weber are passing through a coil of 100 turns. If the EMF induced in the coil is 1.5 volt, the time interval will be. It's a direct question actually. We have to find the time interval. So from here itself we can do this EMF is equal to negative d phi by dt. And if there are n number of turns, you should multiply with n. So it's magnitude only you consider, then dt is equal to n d phi by E. Here number of turns is 100 and the magnetic flux phi is given by 3 into 10 to the minus 4 and EMF is given by 1.5. So if you substitute it 100 into 3.5, 3 into 10 to the minus 4 divided by the voltage induced is 1.5. If you just solve this one, you can get the concept like it will be equal to 2 into 10 to the minus 2 seconds. That is 0.02 seconds. The answer is 0.02. C is the answer for this question. So just rearrange the equation. So here n is the number of turns, flux, the time interval, and EMF induced. So if you rearrange it, you will get it. We can check one more question. Like, suppose phi is given as a function of time. Then how to do it? You should utilize to differentiate the function actually. One question like this. The magnetic flux phi linked with a coil of resistance 10 ohm varies with the time t as phi is equal to 8t square minus 40 plus 1. The current induced in the coil at t is equal to 0.1 second is. So here phi is given, flux is given 8t square minus 40 plus 1 and time t is given 0.1 second and resistance of the conductor is given R is equal to 10 ohm. So you have to find the current I is equal to V by R, and it is nothing but 1 by R into d phi by dt at 0.1 second. So you have to differentiate this function first of all. This is equal to 1 by 10 into, if you differentiate this one and at 0.1 second, you will get it as d phi by dt. The magnitude only you have to consider here, 2 into 8, 16t minus 4. At 0.1 second, this will become 1.6 minus 4, that is 2.4. The negatives, the magnitude if you take it. So 2.4 volts. And here the answer is 0.24. So 2.4 you are getting, that is 0.24 amps. That is the current passing through this circuit. And one more question we can check it. Like, if in terms of this flux is not given as a function of time, then you can do this way also, is equal to negative phi 2 minus phi 1. Initial and final values are given and time interval is given. So phi 2 minus phi 1 by time taken. Negative phi 2 minus phi 1 by delta t. That is equation also, you can use it. So basic concept of Michael Faraday's law, electromagnetic induction, is the induced EMF is directly proportional to rate of change of magnetic flux is equal to minus d phi by dt. This negative sign is given by Lenz's rule. So that rule says that the direction of induced EMF or current will be opposite to the change in flux. That's the concept here. Now, see, if you move a conductor, current carrying conductor, through a magnetic field in a perpendicular way, then there will be an induced EMF in the conductor. We call it as motional EMF, is equal to B into L into V. B is the intensity of magnetic field, L is the length of the conductor, and V is the speed with which it is moved. We call it as motional EMF. So any conductor which is moved linearly in a magnetic field, it will experience, there will be an inducing of EMF is equal to BLV. BLV is, we can check one question like this way. A conductor is moving with a uniform velocity of 10 meters per second at right angles to a magnetic field of induction (0.4 into 10 raised to minus 4 Weber per meter square). If the EMF induced in the conductor is 6 into 10 raised to minus 5 volt, then the length of the conductor is, you have to find the length. So in this equation, L is equal to E by B into V. So in the question we have already the magnetic field intensity is given and velocity is given and EMF induced is given. So just you substitute the answer, you will be getting as 15 centimeter. B is answer will be. So directly you can substitute the equations and rearrange it. It's fine. Okay. Now instead of linearly moving this conductor, if you rotate this conductor in a magnetic field, then there will be inducing of EMF is equal to BL square omega by 2. This omega is the angular speed with which it is rotated. BL square omega by 2 will be the EMF. B is the magnetic field, L is the distance, length of the conductor, omega is the angular frequency or speed. This omega is equal to 2 pi f. If linear velocity, sir, you can make it. How many times? So rad per second will be the value of omega in rotating a rod. Fine. Now, in a conductor, in a coil, suppose you pass a current through it. Because of this current will produce a magnetic field around it, and because of this change in magnetic field lines in the same conductor, there may be an inducing of EMF. This process is called self-induction, and the flux produced will be equal to L into I. That how much current is there, that much magnetic flux will be produced. Phi is proportional to current I, and a constant L you can introduce there. This L is known as self-inductance. Henry is the SI unit of self-inductance. And in this coil, the EMF induced E will be negative L di by dt, rate of change of current You have to cut into L will give you the EMF E induced. For a long solenoid, the expression for self-inductance L is equal to mu 0 mu r n square A by L, where mu 0 is the permeability of free space, mu r is the relative permeability, n is the number of turns, A is the area of the coil, and by L, per unit length L. The self-inductance L can explain L is equal to phi by I also. Flux per unit current I, phi by I. Self-induction is a phenomenon in which an EMF is induced in a conductor coil due to the varying magnetic field produced by current in the same coil. Self-induction. How much energy is produced or stored in that self-induction during the process? U is equal to half Li square. Half Li square is the energy stored in this coil. It will be in the form of magnetic field actually. Self-induction. So induction coil works on this principle. Now if instead of a single coil, if there are two coils present bound one over another, like another one coil is kept inside it, bound one over another, then through one coil, if current is passed through it, in second coil an EMF will be induced, and in second coil if a current is passed, in first coil one EMF will be induced. This will be called as mutual induction. So the inducing of EMF in one coil due to magnetic field produced by current passing through the nearby coil is called mutual induction. We can have the mutual inductance of two coils. M is equal to mu 0 N1 N2 A by L. Mu 0 is the permeability of free space, N1 is the number of turns of first coil, N2 number of turns of second coil, A is the area of cross section of the second coil by L. The interior coil A is taken as. From this we will get mutual inductions. We can do one question like this way. If a current of 3 ampere is flowing through a primary coil is reduced to 0 in 10 raised to minus 3 seconds. The induced EMF in the secondary coil is 15,000 volts. The mutual inductance between the two coils we have to find out. So here we have current of 3 ampere is flowing through primary coil. That's reduced to 0 in 10 raised to minus 3 seconds. We can make use of the basics of this concept. Here we have E is equal to M into di by dt. The magnitude if you take it. This M is a mutual inductance. Di is a change in current and time taken. You can have this way also. M into I2 minus I1 by delta T. That is magnitude of EMF. So the question is given current 3 ampere is changes to down and EMF is given 15,000 and if you do M you will get 5 Henry. So M will be equal to 5 Henry here. You substitute it. Answer is A. That's a mutual induction. So these all are the major concept of the chapter electromagnetic induction. We have Faraday's law, Lenz's rule, and the magnetic flux concept, self-induction and mutual induction. Some more questions we'll do in the practice paper. So please watch the video and make it thoroughly. See you all. Thank you for watching.
Bright Education Center, Medical and Engineering Entrance Coaching Center, Hilal area, Doha, Qatar. For further enquiries, contact 306000679.